So originally the plan was to talk more about reinforcement learning, but I thought since I only had one lecture to give, I think this class would be a little bit incomplete without saying something about multimodality, which is so pervasive if you look at all the major models. So this will be an overview of multimodal models. Of course, this could be a whole class in itself, and I'll try to do what I can in one lecture. Okay, so let's dive into multimodal models. So far in this class, we have exclusively focused on language models. And language models are already pretty general. They give you the ability to go from any piece of text to any text. So this could be any language, code, poetry, anything you like, even let's say DNA, for example. But the world is multimodal. You have text, you have images, audio, video. And if you think about a sort of a North Star of where we want to be, is what people call an omnimodal, which is ability to take any combination of any of these modalities and output any combination of any of these modalities. So for example, I can give you an image and a video, and I can ask a question about about the image and the video. I can generate images. I can convert the audio into an image. You can imagine all sorts of different applications by having an omni-model. So, in this class, I'm not going to build up to a whole omni-model, but I'll give you, some of the pieces that are at least allow you to ingest a little bit of images, which we'll mostly focus on today. So how do you build such a thing? Well, this is sort of a weird way to motivate this, but the reality is that transformers work really well, and despite the best efforts of people to try other things, those are across all these modalities still at scale the best thing we have, so we have to figure out how to use them. And now transformers were designed for text, so they have this property that they speak tokens. So they take input as input a bunch of tokens and then output some tokens. And here I'm sort of expanding the notion of token to be not just a discrete token that we've seen in text, but also potentially continuous tokens. You can think about these as embedding of tokens. And the key thing is that a token should represent some sort of semantic unit of information. For example, in natural language, tokens are subwords, and these are somewhat meaningful. Whereas, for example, a pixel is certainly not meaningful by itself. So somehow we must convert everything, including audio and images, into either discrete or continuous tokens. Now, notice that we've already had to do this even with text. Right? In the first lecture, we talked about tokenization. And there it was not too bad. I mean, we had a BP tokenizer. You guys implemented it. It was, it's fine. One could wish for, a better tokenizer or no something that doesn't have tokenizers at all, but it's not the worst thing in the world. Now, for non-text modalities, we have to scratch our heads a lot more and figure out what is the equivalent of the BP tokenizer that will take an image and produce things that a transformer can digest. Okay, so you have to answer two questions here. One is for non-text data, for example, images or videos or audio, how do you input these into the transformer? And then how do you generate them out? And this lecture will mostly focus on question number one. Okay. So let's start rewind the clock back to 2021. So the CLIP model, which some of you might be familiar with, is a lot of the foundation of modern VLMs. And so we can go through this a bit in more detail. So CLIP stands for Contrastive Language Image Pre-training. And a bit of historical context is around that time, GPT-3 had already happened, GPT-2, all the language models had already gone into this kind of foundation model era. Vision was still there were some efforts, but traditionally had been based on large annotated data sets, such as ImageNet, and training models such as the ResNet on these data sets and doing a bunch of other things like data augmentation and getting really good performance. And so the researchers at OpenAI were wondering, is it possible to leverage the large amount of image and textual captions out there? So inspired by this idea in language where you could just scrape the internet, you have all of this text, it's very noisy, but somehow if you train a large enough model, you can make sense out of this and generate something useful. So what was the equivalent of that for images? So as a result, CLIP was born. And the idea of CLIP is fairly simple and straightforward. So the idea here is that suppose I give you a bunch of image text pairs. So let's say I give you 32,000 of these. Okay? So what I'm going to do is for each image, I'm going to encode it using an image encoder, which I'll explain later, into a vector. So I'm going to have 32,000 of these image encodings. I'm going to also do the same thing with the corresponding text. So that will give me T1 through Tn. Right? So these are the embeddings of the text. These are embedding of the images. Now, the objective I want to set up is that I want the image. Let's take I1. So I1 is associated with aligned with T1, right? So I want this alignment, the dot product between these two embeddings to be much larger than the dot product between I1 and all the other texts. Okay, and conversely, I also want for this text to say that this dot product is larger than the dot product between T1 and all the other images. So that in a nutshell is the CLIP objective, and you can imagine there's basically 2 times n different kind of softmax classification problems. So here's the code. So you get a n by d a matrix for the image encodings and n by d times for the textual embeddings. You normalize, and you take this dot product with some temperature, and then you compute the cross entropy. Okay. So it's basically like a multi-class classification problem where the examples are sort of structured in this kind of n by n matrix form. Okay. Any questions about that? All right. So this some more details about how CLIP was built. So where does the data come from? There are not too many details in the paper about the data. Roughly, it's you take a bunch of queries from somewhere, and then you go search online for these, and you mine a bunch of image and text pairs. And this resulted in 400 million image text pairs. The data set wasn't released, but there was an effort by this paper called OpenClip, which replicated and further kind of extended the CLIP ideas. So there was this data set called Lion 5B, which was released, 5 billion images with textual descriptions, and there was a bunch of processing that happened. Interestingly, they actually used CLIP for the data filtering and then trained OpenClip. So there's some bootstrapping happening, but at least this is a model where you can point to the data set that it was trained on and the code as well. Okay, so a few other details. So images come in all sorts of resolutions, right? If you find an internet image, it might be long and skinny or tall. Long and skinny or the other way. So arbitrary dimensions. And one thing that you learn about neural nets is that they don't like things to be dynamic. They want things to be, fixed size. So there is a sort of somewhat heuristic processing that happens. Is they resize the image so that the shorter side is 336 or whatever target size, could be 224 as well. And then they center crop to get a square. Okay, this is obviously for convenience. Later we'll see that you can do much better than this, but this is just for expediency. And also at this time, the CLIP authors were thinking about ImageNet and classification. So usually the object is in the middle and you're just trimming off some background. So it doesn't matter too much. Okay, so what is the vision encoder? So this is the general algorithm, but I haven't specified what the image and text encoders are. Yeah.
And text when they have an input, right? So they provide text because every type of image generation that we follow will have some sort of trend into it. That's why they train on both text and image pairs rather than just images.
So the question, I think, is why they train on image text pairs as opposed to images. Right. So there is a line of work that tries to encode images into representations based on data augmentation. So for example, if you take an image and I think this idea called SimClear, you augment it, you crop it, you randomly perturb it, rotate it, and you want to say that that is the same image, like they should have similar embeddings. And that's useful for kind of low-level details, but the problem is that you won't data augment your way from like one type of dog to another dog. So by using the text, it gives you higher level semantic representations of the images. And yeah, that's a good question. And later we'll see how these semantic representations are useful if you look at the types of tasks that people are trying to solve. Okay, so what is the vision encoder that CLIP uses? They actually experimented with a bunch of different ones, ResNets and vision transformers, which had just come out. And they found out the vision transformers perform the best, so when people say CLIP, they usually mean the VIT version. And so, a vision transformer does the following. So you take an image, and you break it up into these patches. I think the original paper was like 16 by 16, but CLIP used 14 by 14. But anyway, you have these little patches, which are basically vectors. So each patch is, in some sense, a token for this vision transformer. You add the positional embeddings, just like you would if you're training a language model, and then you just put it through a standard transformer. And if you want to classify, then you would you would usually want to okay. So the transformer encoder produces a sequence of vectors, right? And the CLIP paper does something a little bit different. You can average all these vectors. That gives you a single vector. But they saw it was better to do attention pooling, which means that you take the global average of all the activations, but then you also do another round of attention with that query against the key and values of each position. And that gives you another vector, which is maybe a little bit more informed rather than just like a straight up average. Okay, so that's the VIT. And the CLIP paper found that the best model is what is called VIT-L/14. So this, to decipher this is a large VIT. I think it has like 24 layers or so. not quite sure about that. And 14 by 14 patches. Each patch is RGB, so it has 3 channels. And they trained on 336 by 336 resolution images. Actually, they trained on lower res, and then they and then I guess for speed, because high resolution images takes longer. And then for the latter part of training, they train on higher res. Yeah.
Yeah, for the position embedding, would it be more complicated than in text? For example, text only has like 1D dimension, but image has 2D up and down, like.
Yeah, so the question is, can you be smarter about the positional embeddings, because this is just linear 0 through 9. I think in this paper they actually, in a clip paper, I believe they tried some 2D version of this and the 1D, and they found that it doesn't really kind of matter that much. I think it's also, I always have to take these results with the idea that they're interesting classification in mind. So for classification, maybe it doesn't matter. Later, we'll see fancier positional embeddings that do take into account the spatial structure. Okay, so the text encoder is a standard transformer. It's a GPT-2 style transformer, since that was from the same group that developed GPT-2. And in order to get a single vector out of a sequence, they prepended BOS and appended EOS, and then they took EOS, the activation at the highest layer, as the representation of that whole sequence. Okay, so you have the vision encoder, you have the text encoder, and then you can do this process to train. You pick a batch, you encode all the text, you code all the images, and then you form these two-end cross-entropy losses, and then you go from there. Okay, so the headline result, and which got a lot of people excited about CLIP back in 2021, is that on the ImageNet benchmark, zero-shot CLIP outperformed a ResNet that was trained on 1.2 million ImageNet images. So if you think about this, 1.2 ImageNet images, this was many, many hours of Amazon Mechanical Turk worker time to do this annotation. And now you have CLIP that was trained on more organic web data. Of course, this was the labor of a bunch of people on the web, but if you're able to leverage that or existing data already, then you can just zero-shot it. And the zero-shot technique is basically, to explain it, I don't have slide support here, but you take an image, and then you have a bunch of text, and then you basically take the dot product with the various labels and see which one's the highest. Oh yeah, it is. Sorry. It is on this part of the side. Okay. Good point. So this is a zero-shot prediction, where you take an image and then what I said. Cool. Any questions? Yeah.
Linked to this type of self-supervised learning, would that be an issue if, for example, there's a dog image, and then like with the caption, like maybe not just this single caption, not this dog, maybe other captions are also dog. Would that confuse the model?
Yeah. So the question is, if you have a dog and there's maybe other captions that also have dogs, would that confuse the model? In general, this process is going to be noisy. It's okay if there's another dog, because on average, it's unlikely that there's always going to be a dog. Sometimes it's going to be an apple or a cat or something. But also another point is that these images are basically scraped from images on the web with textual text next to them, or in the alt kind of image, and so they're extremely noisy. There's been studies that look at when you have a caption of an image, it doesn't necessarily just like verbatim say what's in the image, right? Because if you have an image and it's a dog, you don't need to say a dog. And it's, so this process is very noisy. So it's maybe kind of somewhat surprising, but also interesting that it works. I mean, there was a lot of data filtering that is needed. So if you take arbitrary images and text on that web, it's probably going to be way too noisy. One other thing to note, which relates to a point I'll come back to at the very end, is they also tried this alternative where instead of doing this ranking, they can predict text from the images. So they can set an objective where they try to take the images and predict the text, either as a bag of words or as a language model. And they show that, maybe, I don't know, somewhat surprisingly, that if you use a stronger model, it actually does worse, or at least is less efficient compared to using bag of words, clip. So this is saying that I think saying that for the representations that you're trying to learn, or again, this is ImageNet accuracy, so it's classification, actually modeling the exact token sequences of the caption isn't so important for getting the rough representation of the image. Okay, we'll come back to this point at the end. So what do we learn so far? So we've encoded images using CLIP, and it captures the semantics of the image because it's paired with text, and generally text talks about the semantics. It is important to note that the design decisions here are based on image classification, so it's not very fine-grained. But yet it still, as we'll say, serves as a kind of robust starting point for everything we're going to do later. One technical kind of downside of CLIP is that it does require large batch sizes, like 30,000. If you have a batch size of 1, clearly it doesn't work, or even 10, it doesn't work. And furthermore, the softmax operation operates over the full batch. So it's not really very decomposable. Whereas if you think about normal language model training, a batch of examples, all the sequences kind of parallelize, and you just do a aggregation at the end. So this point will be addressed by another paper from Google that came out called SigClip. And so think about this as basically an improved version of CLIP. So it stands for sigmoid loss for language image pre-training. And here the main difference is that CLIP does multi-class classification. It says, I have this aligned text and image, and I'm going to say this is positive and against all the other alternative images or against all the alternative texts. SigClip, in some sense, is a lot simpler. It basically says, for any given image text pair, are they aligned or not? Right? So if I reference this diagram up here, it's basically binary classification where the diagonals are positive examples and the off-diagonal are negative examples. That's it. So here's the algorithm. You take the embeddings, you normalize, you take the dot product as usual, but now you're you're forming the labels which are -1 on off diagonal and diagonals you have 1, and then you do a log sigmoid. So the objective is very simple. Yeah.
Do they require specific sampling strategy? Because I think most of the samples are not along weight. So if we randomly cycling, then maybe the loss I think will be very unstable.
Yeah, so the question is, does this require any sophisticated sampling strategies? At least in the initial paper, they were just operating on literally the same type of matrix. You could imagine, I think we were probably thinking in general for kind of these contrastive methods, like the negative examples need to be, sometimes you need to balance the positives and the negatives, or the negatives need to be like tight negatives so that you're not biased. But at least in the initial version, this was fairly just straightforward. So to speak about the data, this was done at Google. This was a data set. They used another paper, which was another language image model around 2022, which got a web LI data set with order billion image text pairs. They also did some extra work. For example, images that had text in them, they did OCR, and that's another way to form text-image pairs. And did some filtering. This was multilingual. The main point of this paper was that it was much more efficient to train than CLIP. So CLIP was trained 10 days on 256 TPU v3s, and SIGLIP was 5 days on 32 v4s. And you might think, oh, v4s should be faster than v3s. In terms of flops per second, they're actually not. They're better because you can put more of them in a pod, and the interconnect is better. But at this scale, it's really actually, not faster. Actually, like 60% slower or something. So the way that this is faster, and of course, I think CLIP probably did not try to optimize the code for the maximum throughput. It was just kind of, let's get this thing to work. But the SIGLIP paper showed that you can parallelize this as follows. So you have basically, if you recall your kind of systems lecture, so this is, you can think about it as DDP if you like, where each device is stores a subset of the image text pairs. However, there's interactions between the examples, unlike in language model training, where everything just factors. So in the first pass, each device just computes all the losses on its whatever image text pairs it has locally, and then you send the text. So basically, device 1 gets T5 through T8, and now it's able to compute the negatives here, and then it gets T9 through T12. So you kind of rotate around until you cover all the off-diagonal block entries. Another thing that was nice about SIGLIP is that you're effectively decoupling batch size from the loss. Whereas in CLIP, the loss is tied to the batch size. If you change the batch size, it's a different loss function. So they were able to experiment with much smaller batch sizes, less than 16K, and in that regime, it's much better than CLIP because the loss function, if you have too small of a batch size, is just degrades. Whereas for smaller batch size for SIGLIP, you have more variance, but it's the same in expectation is the same loss. They also say, wow, you can go up to much larger batch sizes, but that doesn't really help. And we saw that critical batch size is at some limit, and 32K was essentially their critical batch size. Okay, so now we have CLIP and SIGLIP. These are image encoders that take an image, in this version, just a fixed size image, 336 by 336, let's say, and maps it into a vector, okay, which contains some semantics. So now let's start building VLMs, vision language models. And I'm going to talk about two families of models, Lava and Quen. The two are very similar in the sort of broad template. There are some details that are different, which we'll go through. And the basic idea is that we're going to take these embeddings and then just inject them into a language model. So this is going to be more of the flavor of sort of mid-training or post-training, where we take an existing image encoder, we take an existing LLM, and then we're going to kind of stitch it together rather than training something from scratch. Okay, so Lava paper came out in 2023, and this got people excited because around this time, all the closed models like GPT, I think it was GPT-4, was able to do kind of visual reasoning, and they were able to show that they could do some visual reasoning as well. It wasn't as good as GPT-4, of course, but I think it was an open model, and people got to see what went under the hood. So for VLMs, there's essentially a few pieces here. There's a vision encoder. They use CLIP here. For the text decoder, they use a language model called Vicuña, which is the first Llama model that was fine-tuned on some shared GPT conversations. So these are conversations that people had with ChatGPT and shared them on this website. I don't think this is up anymore. So the data that they used was based on MS COCO. So this was an annotated data set where they had Mechanical Turk workers go and annotate a bunch of images with bounding boxes and captions describing what was in the image. So they basically synthesized a data set for their model. So they prompted GPT-4 with the captions or the detected objects and asked GPT-4 to generate questions or conversations. For example, this is an image in the MS COCO data set. This was an annotated caption done by a human, and also here is the, also annotated by a human. And then you ask GPT-4, generate me a conversation, and you might get a question and an answer. You might ask GPT-4, generate me a detailed description. It generates something, I guess, similar to the caption. And then you can ask GPT-4 to generate complex reasoning, and it does something like that. Okay, so this is synthesized data, 158,000 examples. And then they trained a model on this. So the model, so they use CLIP, in particular the highest performing CLIP version, VITL/14. So 14 by 14 patches. And then let's just look at this image. So they take images, they send it through this vision encoder, CLIP, that gives you a vector. But this vector isn't really in the same space, so to speak, as the text. So then they multiply by matrix W to get another vector, which is in the same space as the text embeddings. And for text, you basically just use your standard embeddings to get vectors. So what's basically happening is that the text gets encoded into these vectors, and the image also gets encoded into these vectors, and then these vectors, this whole sequence of vectors just goes through a standard transformer and produces output. Okay, so we're in some sense converting these images into textual tokens, so I can leverage the pre-trained language model. So to train this model, they do it in two stages. The first stage is that they freeze the vision encoder and the language model and only train this matrix W. And this is what they call the alignment phase, which is essentially making sure that the image gets mapped into kind of the same space. Because if you just use a random W, these images are not going to be, certainly they're not embeddings representing any sort of natural language token. So the goal of training W is that they sort of look like natural language token embeddings. And the second stage is that they now still freeze the vision encoder and then train W on the language model. So they're fine-tuning the language model on their data. So remember, their data is basically, here's an image, and here is a conversation or description or a complex reasoning example. So this is all image plus text to text. Okay, so this is one example from their paper, which is kind of interesting. So you have an input image and a conversation. The user says what's unusual about this image, and their model is able to tell you that you don't usually iron on the back of a minivan. And they also make a point that their model is pretty good because even if your user prompt is not really prompting like the unusualness, it still talks about it. Whereas GPT-4 obviously is able to do this, but other models at the time were not able to. Okay, any questions about Lava? Okay, so that was 2023, and I'm going to sort of skip forward to Lava 1 Vision, which is 2024. There was a sequence of papers after the Lava paper came out of Lava 1.5, Lava Next, and the main, but I'll capture all of these innovations, I think, in what I'll describe next. The main thing that they did is it's essentially the same recipe, but they were trying to be more ambitious in terms of the types of multimodal applications they could do. So they were able to handle multiple images and videos. So here's the same sort of diagram. Now they can take an image, a single image, or multiple images, or a video, which is essentially a sequence of images corresponding to a sampling of the frames. And here the vision encoder, they upgraded to SIGLIP. The text decoder, they use Qwen 2 now, which was probably the best language model that was out at that time. And then for the projector, or the adapter, which is the thing that takes the output of the vision encoder and turns it into the input of the language model, is a 2-layer MLP instead of a linear projection. Okay, so relatively, it's like you have a system and you're just like upgrading the parts, but it's the same kind of rough system. So let's talk a little bit about data processing. So one thing that they wanted to do is to do OCR. And the thing with OCR is that you need to preserve very fine-grained information. Otherwise, a J looks like an I, and that's not good. So remember that clip resizes and crops to 336 by 336. And clearly, if you have a document and you crop to 336 by 336, you can't read it. So their solution is this idea called AnyRes, which was actually introduced in the Lava 1.5 paper. And the idea is basically, it's fairly straightforward. You break up an image into multiple pieces. And the idea is that each piece is the resolution of whatever the vision encoder is going to take, 336 by 336, for example. So you're going to code all the pieces, and then you can into a bunch of vectors, and then you concatenate the vectors. Okay, so you're basically noticing that your vision encoder can't handle high resolution. So rather than downsampling, you're just going to crop and look at different parts of the image. And now if you have really super high resolution images or videos, then you get too many tokens, so then they sort of down sample. But the idea behind AnyRes is that it's sort of adaptive. And this is sort of nice because the transformer is already adaptive. Language can be, your sentences can be any length, and the transformer already handles that pretty well. So it turns out images can be any resolution, so that's kind of picking back off the same kind of dynamic ability. So here is what they actually do for images here. So let's say you have this image of a paper. They do downsample and have one path, which is basically a downsampled encoding of the entire paper. But then they break it up into these chunks, where each chunk is the resolution that the vision encoder expects, and then encodes each of these separately, and then you concatenate all these patches. And if you have too many, then you sort of reduce that the number of patches and by interpolation. So, okay, so then they're able to handle images, multiple images, and video. So you think about, well, all of these are technically all reducible to images, but they put their thumb on the scale a little bit because they want to make sure all the modalities are kind of roughly comparable. Because videos can be very long, they don't want their data set to be dominated by a bunch of repetitive frames. So here's what they do here. So for a single image, they basically have the full image downsampled, and then a bunch of crops up to n crops there, up to 9. And if you are presented with multiple images, then they just use the sort of the base resolution. So if you have a single image, I get to look at it more carefully. If I have multiple images, I'm just going to look at it kind of from afar. And for video, we're going to use even kind of lower resolution or fewer tokens to represent each frame, because the idea is that, well, videos can be, they only use up to 32 frames, but you start running into kind of context length problems for video. And later we'll see how a big part of being able to handle multimodal is to deal with long context. Okay, so the data here that they use is I would say that they state the philosophy is they want to curate high quality data and quantity. Another way to interpret this is that it's very targeted data. If you look at many of these, it's very task-based, whether you're doing visual question answering or answering questions about tables. So this is definitely kind of post-training territory where you're trying to get your model to do these tasks, and therefore you create a bunch of these tasks. And this work is also unabashedly basically distilling GPT-4 models so that they can get the best performance, which is I guess not ideal, but this is what you do if you don't have a annotation budget. So they have single images, multiple images, and videos. So there's a lot of different pieces. Some of these are very specific, like you give 2 images and you're trying to spot the difference. But one thing that I'll come back to this at this point later. So for training, it's roughly the same idea as before, where the first stage is that you're focused on alignment. So in particular, you only train the projector, which is the adapter. And then in the second stage, you train, and the third stage is you train the full model. And before we had 2 stages, now we have 3 stages. I think, I'm not sure there's any particular principled reason for this, except for the second stage is trying to put high quality data, but more focusing on knowledge. And the final stage is focusing on examples that look like your downstream tasks. Okay, so one thing that they found in this paper, which was kind of interesting, is that you get transfer between modalities. So even though they have only single image data for diagrams and charts, but this actually generalizes to the multiple images. So at test time, at training time, it never saw an example where you have a table and a chart and you're asking questions about it. But at test time, you have you have 2 images, one for the table and one for the chart, and you're able to have some sort of conversation about it. At training time, you only have OCR data on single image data, and you only have relational reasoning from multiple images, but you can generalize to these cases where, which are useful for powering GUI agents, where you show it a bunch of screenshots. This is multiple images, and it can generate a description of the screenshots. Another example is that they have this idea of visual prompting, where you have this circle, which is a part of the image, but that's meant to highlight the part of the image that you're supposed to do something about. And this type of data only exists for single images, and now it can generalize to videos where the user says, describe the player highlighted in the video, and this player is across multiple frames. So this is, when I first look at this, and I said, oh boy, you're basically targeting each of these tasks. This is kind of like supervised learning, but if you have enough tasks, these models seem to do some transfer, which is I guess reassuring. Okay, so again, this is a fairly standard VLM template: vision encoder plus the projector into the language model. There's a lot of work that goes into the data curation. They lean pretty heavily into synthesize task-specific data. The nice thing about the Lava series is that it's one of the few works that open sources their not just the model weights, but also the data, so you can really replicate and study this stuff. Okay, now let's talk about the Quen models. So Quen started also training in 2023, multimodal models. So the first version was Quen VL. And hopefully I'll go through this quickly because you hopefully see the pattern. The vision encoder, they used OpenClip. Remember, OpenClip was the open reproductions of the clip model. So it's basically a clip encoder. And for the adapter, they did one layer of cross attention, incorporate 2D positional embeddings, and maps to a fixed size of 256, which is a little bit, I guess this will be changed later because this is definitely not very dynamic, but neither is the vision encoder at this point. I guess this got caught off, but the special tokens are like they have an image tag and a box tag for bounding box and a ref tag for description. This is what happens when your slides are in HTML. So for training, they have 3 stages, just like with the Lava models. In the first stage, the idea is to, they call it pre-training, but it's really, you're not pre-training from scratch. This is generally large-scale, low-quality data. They freeze the language model and train the vision encoder and adapter. So this is a bit different in that from the Lava models in that they train the vision encoder at this point. And you can see some of the data sets that they are training on, 1.4 billion examples. Stage 2, they move to higher quality task-specific data, and you can see some of the kind of the usual suspects of like VQA data sets, chart question answering, and so on. And then they train all the parameters here. And finally, stage 3 is instruction tuning data. You freeze the visual encoder and you train the adapter and the language model. Here are some examples of the type of things that they're able to do. So, of course, this is Quen, so some of these examples are in Chinese. Their interest is also making a model that is supposed to be subsuming a language model. So a language model can do code, so we want the vision model to be good at code as well. And you can have this example, if you can see it, is an image, and can you find Spider-Man and the Hulk, and it can output bounding boxes as well. It doesn't actually output an image, it just outputs a bounding box. And then you can do OCR, you can compare, so usual stuff. Okay, so then Quen 2 was, again, a kind of an upgrade. There's some new ideas here, which I'll go through. So use a larger vision encoder. They also started doing dynamic resolution. I think this was the main thing. We remember when we went from Lava to Lava 1 Vision, they realized, we need to handle images of different sizes. And if you try to do video, it's clear that you need some sort of dynamic resolution. So the model is basically, so let's say you have this this picture here, that might be mapped to 11,000 tokens. This tiny picture of an equation might be only mapped to 8 tokens, and so on and so forth. So how do they do this? Well, basically each, it's a kind of the same idea of the AnyRes idea from Lava, where each 224 by 224 patch is encoded with a VIT. And remember, the VIT that they started with is the open clip VIT, but this gets fine-tuned. And then they trying to reduce the context size. They compress every 2 by 2 into 1, so that they ultimately every patch generates 66 tokens. For videos, they sample 2 frames a second, but max out at 16,000 tokens. Okay, so one thing, coming back to this question about positional embeddings, so they did do something different here with Qwen2. So they used this idea called multimodal rotary, multimodal rope. So remember we saw rope before, and the idea behind rope is that you have a embedding such that the the inner product between the vectors kind of depends only on the kind of distance. So the distance is defined in 1D by just the number of tokens you're away from it. So now the multidimensional version is essentially the same thing, except for now you have 3D. So you have height, you have width, and you have time. So each position, each patch now is a triple defined by the coordinates. And then to compute the M rope, you basically, for every dimension, you compute the rope, and then you concatenate. Okay, so it's a fairly straightforward idea. Although later with Qwen3, we'll see how this is actually a bit suboptimal. Okay, so they initialize the language model with, this is the Qwen VL model, so of course they're initializing with Qwen. And then they have 3 stages of training, which is very similar to what we did before. And then they were able to show a bunch of different capabilities, some video understanding. It can do math and code, function calling, and so on and so forth. Okay, so quickly I'll talk about Qwen3. So again, there's a few kind of changes here. I wouldn't say these are kind of structural big changes, but they're probably changes that do impact the quality of the model. So this is from last year, Qwen3 VL report. And so it's roughly the same diagram here. I'll point out I'll come back to this diagram. I'll go through some of the changes. So one is that now they're using Qwen3 models. They have a series of dense and MOE models, and the Qwen3 models are really, really good, and it really helps the quality of the final model. One thing that they're invested in is long context understanding, so their context length can go up to 256K, which is really important if you're trying to do long video. Let's talk about the vision encoder. So they use Cyclip 2, which is basically an improved version of Cyclip. It's actually an identical architecture. It's designed to be backward compatible. And then they improved their rope. And the way to explain this is before you had the 3 dimensions, time, width, and height. And basically Qwen2 basically allocated the first block of dimensions to the time, then the next block to width, and the next to height. And the problem, if you remember rope, is that each component represents a different frequency. So this would mean that maybe all the temporal dimensions are low frequency and all the height dimensions are high frequency. So they basically interleave them when they realized that, and they now all the the axes are exposed to both low and high frequency. Another thing they did was explicit video timestamps. So if you look at closely at this, sorry, this was, wait, okay, this was Quen 3. Oops. So if you look, this is probably a little bit too small, but before, the timestamp was kind of implicit in the positional encodings, right? Each frame in a video intrinsically gets a different, there's a notion of time just because it's in a different position. But here they made the time explicit. So these are actually tokens. 0 seconds is a token that is now you have a token that represents the time. And they found this to be helpful, presumably because it's something that you can directly refer to, like what happened at after 2 seconds. So that is the main one of the main changes. They also did this square root normalized per token loss. So the idea is that some examples that involve video are very long, and some examples that involve a single image are very short. And the normal thing is that every token is treated the same. And this would mean that the video examples are going to dominate. So they basically, the details aren't too clear, but I believe they normalized each example by the square root of the length to basically downweight the impact of really long examples. The final thing that is worth noting, which is interesting, is that they did something interesting with adapter. So remember, the adapter is the thing that connects the vision encoder to the language model, and Lava was the simplest. It was just a linear projection, and then we got an MLP, and we got some cross attention. And DeepStack, which is actually a paper from the DeepSeek team, but Quen used here, is more sophisticated. They noticed that, well, the vision coder already computes a stack of vision embeddings, and we're basically going to add these directly into the residual stream of the language model. Okay, so this is sort of a bit more of a kind of a deep fusion of the vision encoder into the language model, as opposed to the vision encoder is a black box that just outputs a sequence of vectors. Okay, so training is, so they have 2 phases. Pre-training has actually 4 stages. Post-training has 3 stages. So this, you can see that this pipelines are getting quite complicated now. So they first train the adapter. This is the same as all of these models. And then they have 3 stages where they progressively train on longer and longer sequences, from 8K to 32K to 256K. Most of the tokens are in the stages 2 and 3. And then for post-training, they do SFT on long chain of thought data, knowledge distillation, and then some reinforcement learning. At this point, it's really kind of a systems paper. There's a bunch of, I highlighted the kind of the core new ideas, but there's a lot of details that are different. And if you look at the final results, this is a pretty good model. I mean, if you look at these benchmarks as compared to the closed models, Gemini, GPT-5, and Opus 4.1, these numbers are, the bold means that it's the best number in that row. So the Quen models are actually quite strong. Okay, maybe question.
Wondering for the budgeting, so we're going to enhance both video and podcast. How do you measure like the comparison point output for the video and how do you know how do we define it?
Yeah.
This kind of information of a video or
Yeah. So the question is, how do you, what about video generation, and how do you know whether there should be a video or text? So first of all, these models don't generate videos or images. The video, all the multimodal stuff is on the input side. You're always generating text. And so, and then you're always, in most of these stages, except for RL, you're supervising every token. So there's no, LM as a judge or quality on how well the description is working. It's just basically whatever is in your data set. Now with RL, you can play around with different reports. Yeah.
Yeah. I want to ask, is the training of multimodal models harder than training a pure LLM from both the system perspective and perspective? So for system, I think the most bandwidth could be used in loading images, videos, then one bank for the text. And from the algorithm side, I think image videos, they have more tokens than text tokens. So that also makes the model be dominated by video.
Yeah, so the two questions are training multimodal models harder on the system side? And I mean, certainly it's not easier. I think you pointed out that the data sets are larger. Video data is just like, even loading it can be a bottleneck, whereas generally we have not really focused on data loading for talking about language models because it's very, very cheap. So that needs to be taken into account, and all the same principles of making sure that your data loading is happening async with actual computation needs to be taken into account. And the second part was, sorry, what was this second question? Oh yeah, so the videos and images can have more, especially video, have more tokens. So that's one reason we saw this kind of normalization to make sure that we're not giving more weight to video. I mean, you can always downweight. So if you have more tokens, if you don't like that, you can downweight. We talked in the last, or 2 weeks ago, about like data mixtures. So you can always kind of weight things according to whatever makes sense. But there's also a lot of text tokens out there. So I think in general, if you look at, the models are trained on like tens of trillions of tokens. I think there's I wouldn't say that the number of multimodal tokens like vastly outnumbers text tokens. Yeah, I think you were first.
I also have another question about like API training adapter. Since, for example, like the language model has a definition of where how to know how long it is, how you use that information.
Yeah.
Then like to pass how to
Yeah. So the question is, when you do this alignment, how does it know what the language is? The language model pre-trained, and it definitely has to be pre-trained because otherwise it doesn't make sense to align it. So the language model is frozen, and you're just training the adapter to connect the given vision encoder with a given language model. And the way you train it is, well, you pick a token budget, 67 billion tokens, and you just train. There's not a like adaptive threshold here. Yeah.
Also, like about the difference between the number of parameters of the vision encoder versus like number of parameters. So I noticed on this slide that I think this one tool can be have like 607 audio million. For example, the vision encoder has 175 million parameters. But is usually the size of the vision encoder compared to the model usually much smaller than that? Or why you have it so big?
Yeah. So the question is, are the number of parameters in the vision encoder much smaller? And the answer is yes in general. I'm trying to find where is the other place not here. Okay. The reason is that the vision encoder is in some sense doing a very local operation. It's looking at a patch. A patch is very small, and it's just trying to understand the patches. There's not much knowledge, so the patch, we're not reasoning. So most of the capabilities of the model are still kind of in the language model. I'm trying to find the, okay, where, maybe it was up here? Okay, I can't, oh yeah. So if you look at the lava model, so the full, so it's a 72 billion parameter language model. And actually what? Okay, I don't know why this number is. So, oh, sorry, this is 72 million. Okay, so this is much smaller. The projector is much smaller, and the VIT is generally less than a billion, parameters. Yeah, I guess mostly because it's fairly kind of a local operation. I guess that's the easy way to say it. Okay, I'm going to think some other questions. I'm going to try to move on now. So I guess Qwen 3 is a kind of the last vision language model I'll talk about. This got state-of-the-art performance. There's a lot of data work that happens. Not too many details about the data and the data mix in these later Qwen models. So you'll have to look at the lava paper, or the AI2 has a MOMO paper, which I didn't get a chance to talk about, that has more details here. And from Qwen to Qwen 2, Qwen 3, many of these changes were mostly, there's some kind of changes there, but the overall framework remains the same, and mostly it's kind of scaling up, curating more data sets, noticing that your long context isn't, you have to handle long context, and maybe sharpening your image processing and so on. Okay, so I'm going to now jump to something quite different. So there's this paper called Chameleon from Meta in 2024. So far, VLMs encode images into these vectors, and then they inject them into a language model. And because it's a language model, you can only generate text. You can't generate, images. There's many ways you can go about fixing this. You can just take a VLM. You can also attach a diffusion head, and now you can generate images. But I want to talk about this, idea here, which is Chameleon says, what if we mapped everything into discrete, tokens? And in some ways, aesthetically, this is, well, maybe this reflects that I'm a language person. This is kind of appealing. Because now you can analyze and generate images in the same way. Everything is a discrete token. If you want to do, let's say you want to generate, images. You can say here's a text prompt, and then you can, these are more just tokens that you can generate, or you can kind of flip the language and the text around as well. They have these examples, and from the Chameleon paper, you can prompt and say, I'm bored, can you show me some birds? And then it would be text, and then it would be images, and then some more text and some images. So it's interleaved. And in some sense, the vision of an Omni model is that text and images truly live in the same space. And this is accomplished by making everything look like text. That's one way to do it. Okay, so I'll talk a little bit about how this is done. So the thing you need to do now is to map images into discrete tokens. So there's this idea, rather old, from ORD 2017, which is called Vector Quantized Variational Encoder. And the basic idea here is to map an image into a discrete code. And what you learn is a mapping that maps this into a continuous vector. And this gets sort of rounded to the nearest code. So you have a code book which has, let's say, 8,000 codes. So these are like prototypical vectors that correspond to what patches. And then so you pick one of these that's the closest, and that would be your representation. So that's your encoder. It goes through a continuous phase, and then you sort of round it to the nearest code. And now the decoder is you take that code and you try to reconstruct the image. And then you train these VQAEs by basically minimizing the reconstruction loss. There are some other terms that you add because this is not differentiable, which I won't have time to get into. Okay, but at the end of the day, you have 512 by 512 images that are converted into 1,024 tokens, and each token comes from a vocabulary of 8,000. Okay, so now you have basically text, you have your images, which are basically these codes. They train a new tokenizer to now, because now you have different sort of, your data looks different than if it were just normal natural language. The training is now actually very straightforward. This is just normal language model training, right? There's no adapter, there's no turn the vision encoder, or there's just a language model now. So this is the part that's kind of appealing. So there's still 2 stages, but even for language model training, there's usually 2 or more stages, where the first stage is the bulk of training. It's large unsupervised. They have both text and image. And then stage 2, they mix in high quality data. Okay, so this is really great and elegant. There's a few problems with this. One is that they found that the training was not stable. And the reason is that text and images, despite occupying the same space, just behave very differently. So just calling things discrete tokens isn't really, isn't hiding the fact that there's an image living there. And in particular, text tokens, if you think about predicting the next word, this has relatively lower entropy. Most words are kind of predictable. Whereas image tokens have very high entropy. I don't know what shade of blue this exact token is going to be. And so as a result, they found that this training with this kind of mixture led to a lot of the norms of the parameters to grow and to generate kind of loss instability. They were able to kind of mitigate or fix this to some extent via QK norm and Z-loss regularization, which controls the norm growth. So I'm not even going to show the results, but I wanted to highlight this work because there's a certain elegance here, because it's just one model that treats really all modalities the same. But the downside is that it turned out this model was not really as performant, and the discretization definitely loses information. So think about OCR. Again, if you discretize very small print, you're not going to be able to read it anymore. And finally, training with multimodalities is also tricky. We kind of saw this a little bit with the Quen models, and we had to play around with the weights, but this is more exacerbated here. So VAEs were kind of popular for a while, and in fact, many people were using this for image generation. The main reason to do that is, well, you have a transformer. How do you generate from a transformer? You have to generate discrete things, and you basically put all your data into this discrete form. But then diffusion models came out and became popular and viable for generation. So this flavor of method is sort of less popular than it used to be. Okay, so maybe just kind of reflect and summarize here. frontier models these days are expected to be multimodal, or even more strongly natively multimodal or omni models. Unfortunately, there's I think when Gemini comes out or GPT comes out, they are touted as being natively multimodal and handle all these modalities, and in fact they do. But of course, there's no details about how these are built. I think that it's probably some combination of having a continuous encoder because you don't want to lose information, and then diffusion for the generation but that's my speculation. The fundamental challenge, I think, when you're dealing with multimodality is how do you handle non-text modalities? It's also interesting that there's a symmetry between understanding the modality and generation. And there's no one universal encoder, let's say. For example, when we looked at CLIP, you only cared for classification to capture high-level semantics. So these vectors could be fairly small and capture the high-level semantics. Whereas if you wanted to do OCR, or whether you wanted to generate an image, then you need really fine-grained detail. Like you need to, that's why diffusion is so good, because it can really micro optimize the low, high-frequency information. I think in general, when you're dealing with multimodalities, you have to think carefully about weighing them properly. For example, video certainly has lower information density than text, so you don't want video to overwhelm your text. And like I said before, perhaps at least the current best thing is having continuous encoders. It seems like even CLIP, even though it's 5 years old, or similar ideas are still kind of the go-to way to capture semantics of images. Transformers are still there, and then diffusion models, which I didn't talk about, are great for generation. Okay, so I will stop there. That's it for the lecture on multimodality. I guess we don't have any homework on doing this, but if you're curious, it would be, I think, I encourage you to play around with training some of these models.